Hi, today I will be talking about transfer exploration and reinforcement learning, and specifically recent count-based methods. This work was done in collaboration with Victoria Dean, Simone Parisi, and Abhinav Gupta. In reinforcement learning, the agent learns without knowing the dynamics of the world, only by getting feedbacks or rewards for executing actions. But what if those rewards are rare? This problem of agents solving environments where there are sparse rewards is an active research area in RL. One way to combat the sparse reward problem is to define a form of intrinsic motivation for the agent to want to explore its environment. There are several forms of intrinsic motivation. Some methods, such as curiosity, develop forward and inverse prediction models and reward the agent when it visits states that are hard to predict. Other methods, such as ride, reward the agent when it takes actions that change the environment a lot. We build off of a recently developed count-based method called CBET, short for change-based exploration transfer. CBET counts states and changes in the environment and rewards the agent for taking actions that produce rare changes. See this figure to learn more about CBET. First, the agent explores its environment in a task-agnostic way by interacting with objects and determining their interestingness by changes in the environment. In this mini-grid, we see there's a key and a door which the agent may explore. Then, the agent transfers to a new environment where it has a task. The agent uses the exploration policy that it learned from the previous environment to encourage early exploration in its transfer environment, until it learns to solve the task and receives extrinsic reward, at which point it will start to behave more greedily with respect to its task. In this grid world, the agent's task may be to move this yellow obstacle out of the way, grab the key, unlock the door, and go into the other room. Here's a brief overview of CBET. It rewards visitation of rare states and actions that produce rare environment change. CBET also introduces the two-stage transfer paradigm, where the agent first learns an exploration policy from the intrinsic reward, then at transfer time the exploration policy is fixed and used as a fixed bias to encourage exploration while the agent learns a new task-specific policy. We wish to build from this starting place and look for ways to extend CBET. The obvious candidates are to transfer either the counts or the value function in addition to the policy. In this work, we choose to transfer the change counts from the pre-training environment. The intuition for transferring the change counts specifically is that the change counts represent how the environment changes. Learning to maximize rare changes makes the policy interested in interactive state-action pairs. If the agent learns that pushing a button or opening a door is interesting, then the agent will want to remember it. We tested CBET with saved change counts and compared to regular CBET on several MiniGrid environments, and the results were mostly pretty similar across environments. So we will only show results from multi-room N6. In both experiments, the agent was pre-trained on multiple environments, being key corridor, blocked unlock pickup, and multi-room N4S5. In multi-room N6, the agent must navigate through 6 rooms and then go through to the green goal, which is at the end of the 6th room. The top plot is of the interactions per episode, which is a good measure of the agent's exploration. The bottom plot is a plot of the extrinsic return, which is the reward the agent receives when it goes to the goal location at the end of the 6th room. We see here that there is not much difference between the two methods, with standard CBET performing slightly better in both interactions and reward early on. So for next steps, since transferring the change counts didn't outperform standard CBET, we're going to consider different items to transfer, such as transferring the value function. We would also like to move intrinsic motivation experiments to more realistic robotics environments. Therefore, we will start running experiments in the newly released Habitat 2 simulator. Within Habitat 2, there are plenty of opportunities to experiment with continuous action spaces, so we will start looking into extending CBET into the continuous action spaces environments. Finally, I would really like to give a special thanks to my mentors Victoria Dean, Simone Parisi, and Abhinav Gupta. I really appreciate all of the guidance that you have given and the time you have spent working with me. Thank you very much to Rachel Burchin and John Dolan for organizing RIS and making this experience possible. And finally, I would like to thank the CMU Robotics Institute for funding this summer research. Thank you. Goodbye.